Welcome back, everyone. I want to thank Sanahi and Annie, as well as ET staff and engineers for leading that breakout session. We cannot wait to see what you guys have done. I want to hand it back over to you, Lauren, to lead the Q&A wrap-up with two of our college mentors.
All right, guys. So you already got introduced to Annie Zhao, and I just want to introduce you guys to Sophia Yu. She will be the other college mentor leading you guys in today's Q&A and show-off session, as I like to call it, because we really want to see all of your designs. We got to see a couple of great launches in the breakout room. I hope everyone, saved their breath and blew up their balloons again and is ready to launch it for a second time now that we're back in the main room. But I know Annie and Sophia have a wonderful presentation for you guys, and they're such great resources. So they're both in college right now, slash just out of college, and I know Sophia went through aerospace engineering, and Annie went through computer science, and computer science is so closely tied to aerospace. I had to learn a lot of computer science when I was getting my aero degree, and much to my chagrin. So I'm gonna stop talking and I'm gonna hand it off to them because they're brilliant, brilliant resources.
Yeah, hi guys. I'm gonna share my screen real quick. Let me find the desktop. I hope this works and you're not just seeing crazy amount of my tabs. But welcome to your Astrodynamics wrap up. Real quick, Sophia and I are going to give you an introduction about ourselves while we talk through this. We would love for you to start thinking about the things you want to ask us. So this portion of our day is really going to consist of, number one, just as Lauren said, the showing off, right? So you're going to show us what you did. We're going to ask you questions about it. We want to see all of your rockets, good and bad, and talk through them. And the second part of today, or this session, really is primarily focused on asking questions, right? So you can ask us questions specifically about our experience within aerospace, within engineering, within college, high school to college, literally anything that you could think of. We are here as resources. If you even have questions for maybe other ET staff, engineers, we can provide that too. But so as we're going through this introduction, maybe start thinking about the questions that you have related to engineering, related to college, and all that transitioning. So first, my name is Annie. Like I said, I'm currently a senior at the University of Notre Dame. Here at ET, I'm a mentor. I've also worked on some of the labs, not this one, but other ones that you might do, for example, networks or machine learning. I study computer science and economics, so that's a double major right there. And I also recently picked up a minor in Chinese. So if you have any questions about what it's like to study, more than one specialty, how to kind of figure that out, how to pick that, or even like when I decide to pick that, right? Um, I think those are some great questions that you guys should keep in mind. So, just a little bit of background about myself. Now that I am 4 years, from high school, and the memories are getting a little bit, in the past. But essentially, when I graduated in 2021, I had the mindset that I was going to come in to Notre Dame, and I was probably going to be pre-med actually. And in my high school career, I did a lot of prep for pre-med, thinking, okay, well, obvious career choice path. Doctors, they make a lot of money, blah blah blah. Like it's just to me that seemed like just like an easy path. By no means is medicine easy, but in my head, that's what I thought. However, when I start to actually evaluate like the things that I enjoy doing, the type of lifestyle that I wanted, I started thinking it through and I realized that, number one, I really enjoy more like problem set, logical thinking, careers, right? So me personally, I hate reading, I hate writing, I hate these types of more maybe humanities or logistical things. I don't particularly love spreadsheets either, so doing something where I could, solve problems and create things, I think that was where I started to think about. The other side of that was I thought about like my own personal life, right? I think a lot of times we do think about careers and we think about that from an interest point of view, but I think it's, for me at least, it was really important to think about it from a lifestyle point of view too. I knew I wanted something with job security. I knew I wanted to do something that, would make me financially stable. And then even more importantly than that, have a good work-life balance. So, I have had experience that I'll, touch on in, like, for example, the finance world. And although that is extremely interesting, it doesn't fit maybe the particular lifestyle that I'd like to live. So when I came in, I decided, you know what, I'm going to start out as computer engineering for some reason. And it was just a very hot field, right? I ended up switching that to just computer science and then realizing that I had room for economics, which is another just interest that I had. So I double majored in that. Ended up doing a more finance related internship after my freshman year, and that's kind of through that experimental phase where I learned, okay, I actually really don't enjoy the finance industry as much, so maybe econ is just like an interest, The next summer, I actually helped Engineering Tomorrow, the lovely company that is providing all of you these labs right now. I helped them develop their labs. And then, let's see. And then the following fall, so my junior year, I studied abroad in London. And if you guys have questions about study abroad, that's a huge topic too, so feel free to ask later. But while I was there, I was able to intern at Mars Wrigley, which is that huge candy company that makes Snickers and Twix and all of your favorite candies, M&Ms, and I did marketing there. Also just kind of like a trial and error situation. Um, but throughout my college career, I also did some consulting clubs at school, and that kind of led me into testing out tech consulting this past summer at PwC in New York. And I really enjoyed the lifestyle. I enjoyed the things that we were doing. However, I think that, for my future career trajectory growth and what the job entails as a full-time employee, I wasn't fully sure that this was for me. And so then I re-recruited, and actually what I will be doing is going to Chicago after I graduate at McDonald's. And so they have a global technology rotational program, which helps me explore different sides of tech before, I fully have to commit to maybe one side of it. So that's a lot about me. And think of any questions you might have. I could, blabber on forever. But before I blabber on forever, I'm gonna hand it off to Sophia to let her introduce herself. If this will let me, there we go. Oh, no,
Perfect.
no, I don't know how to do this. Does it go back? Okay, yeah.
Go back one more.
One more.
Cool. Thanks, Annie. All right. Hello, everyone. My name is Sophia. And I also am a senior at the University of Notre Dame, and I'm studying aerospace engineering. And I think you guys might have touched on this earlier, but aerospace is commonly broken into two different fields. There's the aero side, so like your planes and helicopters, and then the space side, so rockets, satellites, things like that. While I love the aero side, I think my true passions lie in the space side. So at Notre Dame, I've been involved with a lot of rocketry things. I've had a satellite internship before. So those are where my focuses lie. Next slide, please, Annie. Thanks. All right, so a little bit about my engineering timeline. I graduated high school in 2021. Seems like a really long time ago. I can't believe I'm this old already. And I went to a small high school in Ohio, Northwest Ohio. And similar to Annie, I also was very set on pre-med all through high school. So I did a bunch of clubs geared towards becoming a pre-med major in college. And it wasn't until my freshman year that I decided to switch to engineering. I always really liked space, but I thought that medicine offered a lot of good career paths. So I was pretty set on that. But then during freshman year, I decided to pursue my true passions, which lied in space. And I've always really liked math and science. So aerospace engineering kind of felt like the perfect option for that. So pretty immediately after I got into Notre Dame, I joined the rocketry team. And we're a team here at Notre Dame, and we design, build, and launch a rocket every year for one of NASA's student competitions. So I've been involved with that all 4 years here. I spend most of my time doing that. It's a lot of fun. So I started that freshman year, and then sophomore year, I got my first internship. I studied abroad the summer after my freshman year. So if you guys have questions about that, feel free to ask. So I didn't get an internship until the summer after my sophomore year, and I interned at a company called Maxar Technologies out in Palo Alto, California, right by Stanford. And it's a satellite manufacturing company. And I was working with their electrical team, and we were writing test plans to run on the satellites to make sure they were working properly before we launched them. And I really, really liked this internship. It totally confirmed my passion for the aerospace industry. And it was really cool. I came in at the end of a lot of their satellite programs. So all of the satellites I worked on, we actually got to see launched to space in the same summer. So that was a really cool experience. And then my junior year of college, I was a design lead for the rocketry team. So I was in charge of building all of the payloads for our rocket. Spent a lot of time with that, and I can get into some of the details later on. And then the summer after my junior year, I decided to do research. I really want to go to grad school after I finish my undergrad degree. So I was like, okay, I need to get some research experience. And Notre Dame doesn't have too much of an astrodynamics space research base, but they have a lot of turbo machinery. So I decided to get into that. It's not exactly what I want to do, but just getting in the lab and getting hands-on experience is good for grad school. So I like focused on the aero side a little bit more, did some turbo machinery stuff. And then right now finishing up my undergrad, planning to go to grad school. I applied to a bunch of PhD programs. Haven't made a decision yet, but that should be coming soon. Next slide, Annie. And then here are just some photos highlighting some of the things I've done. Again, a lot of these are from rocketry. I spend most of my time doing that. The rocket in the middle right there is our one from last year, and we actually won NASA's competition. So this is the first time we've ever won. So that was really exciting. It felt like all of the hours of hard work finally paid off. So that was really cool. And then the big satellite in the middle there, that was me at Maxar 2 summers ago. And that satellite is super cool. It's called Jupiter 3, and it's actually the largest communication satellite in orbit right now. So really exciting. We got to watch that one launch, and that was a great experience. And without further ado, I think it's time to hear from you guys. So
Stop sharing right now. And let's get started. I know we have a lot of schools with us today, but if any brave volunteers want to show off their designs first, I know we got some great ones in the breakout room. I don't know if you guys want to just re-show them because they
Annie,
were really cool.
you know what, Annie? Let's go to Academy of Mount St. Ursula because we have ET's own engineer Jerry Dawes there in person today. Academy of Mount St. Ursula, can you guys unmute? I think you guys are ready to launch. Mr. Dawes, are you ready? Yeah, unmute.
Hello, Engineering Tomorrow. Jerry Dawes, staff engineer at Engineering Tomorrow here. I'm at the Academy of Mount St. Ursula in the Bronx, New York City. Bronx News 12 is actually here to do a story about us. The local media is on site, and we have some students that have put together beautiful rockets, and I want to show at least two of the rockets being launched. So bear with us for a quick moment. We've got to move the laptop over to the launch pad. And so bear with me for a quick moment.
Okay.
I can definitely see that there's a lot of room for these balloons to go. I feel like a typical classroom, probably half the height of this one. So really interested to see how high this can
this
go.
is a great facility. I'm excited for this.
Me too. They even have media coverage going on. This is awesome.
This is really exciting. Yeah, I want to see these students launch. We've only got to catch glimpses of their balloons all during the breakout session, but their launch pad was too far away, so we haven't been able to see anything yet.
Very nice. Now, we will keep an eye on you guys while they set up. Is there anyone ready to go right now?
Is it visible? We're ready to go from a different.
I see. That's Mount St. Ursula from a different angle.
If you guys are able to mute that other laptop you guys are using, like turn on the volume, I think by unmuting yourself on the AMS.
Yeah, apologies about that. We tried to get a local laptop to show the launch, but whenever we unmute on that laptop, we get that feedback. So we're going to mute on that roving laptop and then just show the launch. All right.
Perfect.
So bear with me for a quick second.
Oh, this is going to be good.
Oh no.
Oh no.
That's okay.
It was a good launch. Hey, it did launch, you know. went two separate directions, but I think the biggest
apologies, the first launch didn't go so well, but we're getting another one ready. So, all right, give me a few minutes. If you could go to another high school and come back, because we have another rocket ready to go.
Okay, will do. Who's ready next? Challenge Prep, American Senior, Archimedes, Empower College Prep.
Remember Empower College Prep had a really impressive one back in the breakout room. But I know it also takes a second to kind of get reset up. Are there any other?
I have a couple of groups preparing, but maybe a couple of minutes.
Okay,
Okay,
perfect.
sounds good.
No problem. American Senior, you see you guys are moving around if anyone's ready.
Challenge Prep seems like in the breakout room they had some really big balloons ready to launch. So I wonder if they're ready to go.
and I'll wait to see these, and also just to talk to you guys about any challenges you faced or things you needed to tweak and adjust throughout the process, because that's important as well. I think here comes Mr. Dawes.
Yeah, so Jillian, are you ready for me?
Yeah, let's spotlight you.
So I would like to first introduce Laila. She's our team captain.
Hello.
And you can, if you want, you could please ask Laila questions about the design challenges. As soon as you're done interviewing her, we're going to do the launch.
Awesome.
Great. Annie,
All right.
Sophia, what design questions do you have for Layla? Let's hear it.
Nice to meet you. Thanks for doing this. I guess my first question is how many like iterations did you guys have to go through for your designs? Like, did you have to change the way that you designed it multiple times, or did you kind of get lucky on the first time?
We had a few iterations that we went through. At first, we wanted to attach 3 balloons so that all the air was in the center. But then we went with, I believe, 2 small ones and 1 big one in the center.
Cool. And what would you say was the most challenging part of the design process for you guys?
I feel as though the most challenging part was getting the balloons to stick together well because they kept popping. But as soon as we found a way to do it, we came up with our design.
Have you guys
And
been
we
able
had our
to kind of
inspiration.
replicate your results every time?
Yeah.
Okay, awesome. Well, we're excited to see it. Is it on the other one? Should we spotlight the other camera?
Yes.
Go to the other? Okay.
All right, so what we're going to do now is we're going to use a roving laptop to show the launch. That Laila is the team captain, and she'll have her other team members kind of show the launch. All right, so bear with us a second while we do the roving laptop.
There we go.
Those are some big balloons.
Uh-huh.
Reminds me of a hot dog. It looks like a hot dog bun.
Start the countdown.
Good. We can see you. Jerry's counting them down. There's the launch. Wow. Wow.
I don't know if I saw it, but it looked like it went all the way to the ceiling, huh?
Yes.
Anna, that was so cool. That was so impressive.
Thank you.
So were you guys able to see that?
Yes.
We were. That was
awesome.
awesome.
That was awesome.
Congratulations,
Thank you.
guys.
All right, any more questions for Laila?
Oh, I want to
I have
ask
one,
how many,
actually. Oh, sorry, Annie,
go
go ahead.
I was gonna ask how many paper clips you guys got up there.
Sorry?
How many paper clips? Like, how big was your payload?
I think we did about 5.
Okay, nice. Lauren,
Yeah.
go ahead.
So
My
5
question
paper
is-
clips in the payload.
My question for you, Layla, is how does it feel? Successful launch. How does it feel to have that go well?
It feels excellent. I would love to pursue a career in this now.
Awesome. I want to say thank you so much for being the team leader.
Yeah.
Happy World Engineering Day. Happy Women's History Month. And you can do anything you put your mind to. Okay.
Thank you.
Thank you so
All
much.
right, great.
Awesome.
All right,
Yes.
signing out. All right, thank you.
Awesome. That was so
Our
good.
group is
I
ready.
know that challenge prep is ready.
Looks like Archimedes is ready to launch.
All right, let's go. I told Challenge Prep will come to them. And then let's get a little line going here, but Challenge Prep, can you unmute for us? We can see you, we can't hear you. Oh, look at that.
That looks like a great setup.
All right, so it's always, we did it and it went really well. So now it's, of course, we're a little nervous to see if we produce our results, right? Because, so let's get this set up.
Here we go. Somebody screenshot this.
So take a look. You're putting the balloon together. Okay.
Yes. All right. Do you need help?
Yes.
Okay. All right. Ready?
Yeah.
3, 2, 1.
Yes. Lift off. Great job, you guys. That was really good.
Do you guys want to come up to the screen and let our college mentors ask you all some questions?
Hey guys, that was awesome.
Great job, guys.
There you
I think
go.
it's really cool that this design looked completely different from our last hot dog shaped one, and you guys did, just as well, I would say. I feel like, were you guys able to calculate the velocity and the thrust and all of that yet? Or not
Yeah.
yet? That's okay. Well, I feel like if you guys were able to record that, you would get some crazy velocity on it. I guess same question for you guys. How many design reiterations do you guys go through before you kind of landed on this successful one?
Only 2. Yeah, we did it like twice.
Oh, Sophia, you have questions?
Yeah, so if you guys were to do another iteration, what would you change to make it better?
We were probably like making like the balloons more even. Like
Even up.
Okay.
and instead of using like 2 different size balloons, we'll probably use like both of the same size balloons because I feel like if it probably wasn't like for the long one, it probably won't.
Gotcha,
Yeah.
that makes sense.
And then
And I
my
will
question
say
for you guys is, tell me one thing you learned through this lab.
Thrust.
Yeah.
Like how the pressure, like how the pressure like goes, like it's supposed to be at the bottom. So like when you release it, it goes up.
Awesome. Thank you guys so much, and congrats on a successful launch.
You did
Great job, guys.
so well. Are you guys in Georgia?
Yes.
Yes, nice. From the Peach State. Thank you so much, gentlemen. You did an awesome job. All right, Empower College Prep, are you ready?
Yes, we have a group that's ready here, and
Oh,
you can talk to them after they launch, then you can interview them.
okay. Look at this setup, you guys.
You guys
It is
ready?
enormous.
They have 22 grams, I think. Right?
We have
60 grams.
16 plus the pig, all the.
Okay,
So,
go.
Like 36.
Go, guys.
3, 2, 1, go.
Hey, it worked. Yeah.
Yes.
Okay, come on, you get over here, guys. Hey, over here, they want to talk to you.
Come on over.
So introduce
Nice job, guys. That was so cool. Was that your first design? How many designs did that take you?
Quiet, guys. There you go. Talk. Interview. What's your name? Raul.
Hi, my name is Wilson.
I'm Osvaldo.
I'm Tony.
Tony, he's
the
the
side. Hey.
Yeah, there you go.
Well, great job, guys. Really, thanks for volunteering. You guys did a great job. I wanted to ask, is that your first design, second design?
This is like third iteration.
Yeah.
Third iteration? Okay. And were you able to reproduce this result, or is this kind of like, the first time it's gotten that great?
This is the second time we tested this design. So we were able to reproduce our second result.
Nice.
Our first
yeah, I'm
result
gonna
didn't
steal
go.
Oh, go ahead.
I was gonna talk about the first result. It didn't go anywhere because they were using these rocket lamps here, and they weren't very helpful. In fact, it seems like all it did was add mass. Despite
Oh,
there's two of these just going.
oh, interesting. Yeah, I wonder why. I think for some other groups it works out, but maybe for your design, all it did was add mass. That's very interesting. Sophia, do you have any questions?
Yeah, first of all, great job, guys. That was really cool to see. Do you want to walk us through your design process and what your thought processes were when you were coming up with your design?
Oh, okay. We had the thing with the exit, no?
Oh,
If
yeah.
it had a wider exit,
Provide
you
some
think the air
rest.
would go smaller.
Exactly. Is that right?
Yeah.
Yeah. Yeah, explain. I don't know, man. It's just like,
Oh,
it's like,
Hey, Tony was kind of the chief engineer here, so why don't you tell him what you thought, Tony? Your thoughts on that design? Why did you choose those balloons?
oh, it was through the trial and error.
Oh.
We see that those were the ones that really worked, because even with two of these, they didn't lift, but with just one of those, they were able to lift the straw.
Gotcha, cool. And about the opening at the bottom, I think you guys were right on that. If you've seen pictures of rockets before, the boosters will converge and then diverge. So the flow accelerates and then it expands out, and that's how you produce maximum thrust. So you guys were right on that. So good job.
Great
Excellent.
job, team.
I love that they mentioned trial and
Yeah.
error. You guys did an awesome job. And there's just so much gorgeous hair in this shot. Goodness. Good job, guys. Thank you.
Do we have time for Archimedes? I know they're really itching to.
Oh, yes. Let me
Good.
go to them. There we go. Here we go. Let's remove. Hi.
Hi, good morning, everyone.
Hello.
Hi. Just lunch.
Yeah. Ready? Ready when you are. That looks great. What do you think, guys? Is this one going to the ceiling? What do you think?
Got a lot of firepower. I think so.
I hope they're able to open them all at the same time. I think that'll be the big challenge here.
Oh.
Going the wrong way.
Yeah, come talk to us about it.
Hey guys. Well, it was still cool to watch. Don't worry. I guess, was this your first time trying to launch that, or have you guys tried?
Yeah, this is our first time.
Okay. And then having seen that, do you have any ideas of how you want to change your design?
Nah.
It's just the way you.
Just make it smaller, I guess.
Yeah, mass might be an issue. I'd also maybe suggest we have in the guidebook, if you attach a straw to it and then tape like the string from the ceiling like to your balloon, it'll kind of help direct it. So I think one of the big challenges wasn't so much how much power you guys had, but rather the direction of it. But so definitely think about that. Sophia, do you have any questions?
Yeah, on the next iteration, I would try adding the string, because it seemed like you guys have enough thrust to reach the ceiling. Your rocket just went the wrong way. And rockets in real life always start on some sort of guide rail to guide them in the upwards position. So, if you want to make it go straight up, add the string, and that should help a lot.
Okay, thank you.
My question for you guys, real quick, is what happened with the last stage? It didn't release. So do you guys have thoughts on how you're gonna make sure it releases, or was that kind of the intent?
That was the intent.
All right. Well, thank you guys so much. It did have a lot of firepower. It just went horizontal. So thank you.
So good. And I love you all suggestions to them, what to try differently. All right. Anyone else want to come up and share? American Senior, we can see you in there working hard. If not, it's okay.
Yeah, if not, that's all right. We will showcase some of the rest of our presentation real quick. But if you guys do, someone stop me. I'm not sure if I can see the chat while I have my screen shared.
Okay.
Let me find my desk. Too many things on my laptop. Okay, let's get back to sharing. So we just kind of did this discussion. Before we get to the Q&As, I think it's important to kind of talk about the career path in this. I know one person especially mentioned how after doing this lab, they're so excited to kind of look at this as a career path. I'll talk about the first half of it, and then, being that Sophia is, more concentrated in this, I'll let her take over that college part. But essentially, you guys are going to finish high school, right? You're gonna think about what you want to do post high school. Maybe you'll go to college, maybe you'll try to, pursue a different way out. That's completely a personal choice. If you just come out of high school and you want to work somewhere in this space industry, becoming a manual operator is always great. And through this, you can always move yourself up as you learn through the job as well. Another great option is there's going to be 2-year programs. So whether that's going to a more technical school, so getting some sort of certificate in operations and technician, even going to maybe a community college and getting an associate's degree in something related to engineering, can help pivot your way in. But how about Sophia? You want to talk about your experience and what you suggest for the 4-year option?
Yeah, I would love to. So I feel like the most traditional option with engineering is to go with the 4-year option. So that's right after high school, going to a college and getting a degree in engineering. And if you want to work in aerospace, you don't have to major in aerospace engineering. Aerospace encompasses so many majors. There's computer scientists, computer engineers, electrical engineers, chemical engineers, business people, consulting. Honestly, any major can find themselves in the aerospace field. So even if you guys are like, I don't want to do aerospace engineering, but I want to work in the space industry, there's so many other majors you can choose. So don't feel like you're limited to just aerospace engineering if you want to work in the aerospace industry. And then after you finish your degree, there's a couple of options. A lot of people will go get jobs right after. So they'll go right from college and enter the industry and start working right away. And then there's also the graduate school option, which is the one I'm pursuing. So kind of similar to how you apply to college. While you're in college, you'll apply to grad school. It's a pretty similar process. And you can get your master's degree or your PhD. There's a lot of different degree options, but those are the 2 routes after college for a typical aerospace engineer.
Yeah, thank you, Sophia. And we have about 10 minutes left. If there's no other people showcasing their design, we can open up to Q&A now. So you've kind of heard a lot about, me and Sophia, our journeys in college and engineering. So here's some sample questions. If you're kind of struggling to think about what questions you might be interested in us asking, feel free to either unmute your mic or, just type it in the chat. But we're really here to answer any questions. Now we're almost done. We have a wealth of experience.
I've got a question for both of you, actually. It's about designing rockets, either these balloon rockets, if you want to do an outdoor launch, or just, designing rockets in general, which I know Sophia has a ton of experience about. So how do you account for external forces like wind velocity and atmospheric pressure when designing a rocket? And this question is from High School for Health Professions and Human Services in New York.
I can take this one. That's a great question. A lot of times when you're launching a rocket, the rocket is going so fast that you don't really have to consider a lot of the drag forces it will experience. But if you do, a lot of times engineers will run the rocket through a simulation. So on our rocket, we actually have an air braking system. So we have these little flaps that will come out, and it's a feedback controller. So we'll input things like velocity, air pressure, and we'll those things will get run through a computer, and then our little flaps will deploy at certain angles in order for us to like hit a target altitude. So the flaps will control how high we go. In those kind of cases, we'll run it through things like computational fluid dynamics and a bunch of computer simulations. So when you're designing a rocket, you always want to make sure you simulate it before you actually build it and fly it. So all of the things we'll design on the computer before we actually launch it, because you don't want to spend a bunch of time and money and wasted efforts to launch something if you don't know that it's going to work. But for model rocketry, a lot of the kits you can buy, and for most rockets, you don't really have to consider the external forces for the most part.
I think Sophia really covered that. I definitely do not have as much experience in launching a real rocket as she does. But I think, like she said, it's a lot of it's from trial and error. A lot of it is you've done, some rockets before, so you kind of know the new things to account for. Things like simulated on the computer is when it gets more advanced, right? And I think that'll help save a lot of money and time. But are there any other questions right now?
I've got another one for you, Annie. And this is just, kind of combining a couple of the questions that some high schools have asked. You have a computer science background, and some of the students are wondering how different kinds of backgrounds contribute to aerospace engineering. So I know you brought up simulation. Is there any chance you could elaborate a little bit on that and how computer science really ties into all of it?
Yeah, absolutely. I mean, I think so very generally, regardless of what you study nowadays, especially if you're in engineering, if you're in business, you will learn some sort of computer science, I think. Now that AI is such a big part of our industry, now that everything is, done on computers, there is to some extent just like necessary coding background. So Sophia is aerospace engineering, but I know for sure, without even have to ask, that she's taken some sort of coding class before, right? Business majors, my friends are taking coding classes because everything encompasses some sort of computer science. So if you choose to actually even specialize in computer science, you kind of have this very general, broad, like almost like leg up on a lot of different industries, because in every single industry, if you are in some form, have a technology presence, whether that's internally or, as like a platform, you're going to need some coding knowledge. So the way that, I thought about it is like when I picked computer science, it was my thought process was, here's this very general, broad skill that I can learn, really get to know super well, and then that's going to afford me all these different opportunities. I think some people pick computer science because of the love for, the actual coding, for the actual applications there and the creativity that can spawn. I chose it because it affords me a lot of opportunities to actually explore all these different industries. I think there are some, industries that, will prioritize certain majors, but I think computer science is one that if any industry you can name, you can enter if you have a comp sci degree. Specifically with aerospace, just as Sophia mentioned, all these simulations, all these things you have to do online, trying to, program robots and to do certain things when they react to certain stimuli. All of that comes from a certain degree of coding. So, and I'm sure on Sophia's team, there's plenty of people who aren't aerospace majors who are helping out, including computer science majors.
Fantastic answer. All right, I have another question for the both of you. Students, if you have any questions, this is your time to type them in chat. But while you're thinking of your questions, the High School for Health Professions and Human Services had another hard-hitting question. They want to know, is there a minimum IQ required to study aerospace engineering or astrodynamics? Because I joked earlier, this is rocket science. You are studying rocket science. So they want to know, like, do you have to be some kind of mega genius? And how can more people see themselves as future engineers and envision that kind of future?
I can take this one. There's definitely not a minimum IQ if you want to go into astrodynamics or engineering in general. I would say the thing that gets the most people through engineering, because it is a pretty hard major, there's a lot of math, a lot of really technical calculations and a lot of science behind it. But if you're passionate about it, you can totally do it. And like I said before, in high school, I thought I was going to be pre-med. So I did literally no engineering in high school. All of my clubs were focused on getting me ready for pre-med. So then when I got here, I learned everything from the bottom. I started at the bottom and worked my way up. So I had no knowledge coming in, and it turned out to be fine. So definitely not a minimum IQ. And honestly, if you just love engineering, if you love science, if you love math, you'll be fine.
Yeah, I'd also mention I personally don't think IQ is, your end all be all of determinant for intelligence or capability. So, never think in this finite type of scoring system. And before we close out, I know we have one question in the chat asking what inspired you to be an engineer. And so, I know I touched a good bit on, this idea of both what I'm good at, what I enjoy doing, and what type of career progression I like, or career lifestyle I want. So that's what inspired me to kind of first enter the field. This is a very general, like if anybody is interested in engineering, I highly recommend that you start your undergraduate college career in engineering. This is a lot of more technical things that might not be apparent yet, but when you pursue any major in college, there's a certain amount of credits and classes you need to take for this major, right? But based on what major you do, that number and those classes can look very different. So, for example, getting my computer science degree requires me to take a lot more classes than my economics degree. And so therefore you might see a lot of people have dual majors with economics and history and all these different things because the major itself requires less, so they have more time and more space in their schedule to do more. The reason why I recommend you start off with engineering is because it's a lot easier to switch out of engineering and still complete your degree, right? So let's say you start engineering, decide you hate it, never want to do it again, then you want to switch to business, you want to switch to science or whatever. It's a lot easier to switch out and still complete your degree within a timely manner than to switch into it. I also know people who switch into it, their sophomore year, but there's a lot to catch up on, so they might have to overload on classes. They might be taking an extra semester, things like that. So I know that didn't fully answer the question of, what inspired you to do it, but I would really recommend if you have any inkling of interest to really consider starting out at least within the degree, and you can always switch out. Sophia, any last words?
I think you said that really well, Annie. I can kind of answer this one. Honestly, what inspired me to do engineering was my passion for space. So I've always loved space. When I was a kid, my favorite thing to do was go out and look at the moon. So I knew that I wanted to do something that I would be really excited about to wake up and do every single day. So that's kind of how I landed on aerospace engineering. And I think that with whatever major you pick, you just need to make sure that you love it because college is hard, graduate school is hard. There's going to be tough days. So if you aren't passionate about what you're doing, you're going to lose motivation very quickly. So make sure that whatever you pick, you really love it because that's what you're going to be spending a lot of your time doing.
That was so well said, guys. And I can't agree more. Finding that passion is so integral to being able to just pursue any kind of career. And so since we're talking about, passion, I would really like to take this time to introduce our wonderful, wonderful keynote speaker for today, who is an astronaut. I mean, this is going to be so cool, you guys. Like, as someone in the aerospace field, and as you guys are watching this and you've built your balloon rockets already, I hope you're as excited as I am to listen to Andre Douglas. So I'm going to give him a brief introduction, and then I'm going to give him the floor because really we're here to listen to him. So Andre Douglas was selected by NASA to join the 2021 astronaut candidate class. He reported for duty in January 2022. The Virginia native earned a bachelor's degree in mechanical engineering from the U.S. Coast Guard Academy, a master's degree in mechanical engineering from the University of Michigan, Ann Arbor, a master's degree in naval architecture and marine engineering from the University of Michigan. So now we're on 2 master's degrees, a 3rd master's degree in electrical and computer engineering from Johns Hopkins University in Baltimore, Maryland, and then a doctorate or a PhD in systems engineering from the George Washington University of Washington, D.C. First of all, wow, that is so many degrees. So that is so cool to hear that he has a passion for education. Douglas served in the U.S. Coast Guard as a naval architect, salvage engineer, damage control assistant, and officer of the deck. Upon selection, Douglas was a senior professional staff member at the Johns Hopkins University Applied Physics Lab, or the APL, working on maritime robotics, planetary defense, and space exploration missions. Douglas holds a professional engineering license in the state of Virginia and is a champion of youth mentoring and development through FIRST robotics competitions and junior achievement mentoring programs. And it's my special excitement to be able to introduce him today, not only because of his, amazing background. I'm also Virginia native, and I, spent my career, the early parts of it, studying both space and water, as you all can see. So I'm just so excited to see someone else whose passions kind of find that same niche overlap that mine do. And I can't wait to hear from you, Mr. Douglas. So without further ado, please take it away. And I'm really excited for this talk.
Wow, Lauren, we should connect. I had no idea that you were also a space and ocean type person. So maybe after this, we could really talk, because that's super exciting. Really love the energy today on the call. You guys are all pretty awesome in sharing information about engineering and, the passion. I can't emphasize it enough. The last two folks, Annie and I think Sophie, you guys nailed it. Like, passion here is important to do these really hard things. I mean, behind me in my background is what NASA is looking to do. We're looking to go to another planet, right? We're going to use the moon as our launching point, and we're going to a whole nother planet to explore. So there's a lot of will and grit and passion that goes behind that. So I'm super excited to share all of that today with you. The one thing I really wish we had today, honestly, was more time. But I'm gonna do my best to try to make it short. If I go too fast, I apologize in advance, but hopefully you can hit rewind since it's recorded. But I want to get as much content out to you as possible. And I also want to try to make sure we can get some Q&A going for anything specific that you guys have, because I'm an open book, very honest, and love to share. So let me go ahead and try to share my screen for my presentation today. I also have somebody as a backup if this does not work. So let me see here. All right. Share. And then let's go to presentation mode. All right. Okay, can somebody online give me kind of like a sanity check to see if they see the astronaut with the moon in the background?
Good to go.
All right, awesome. Awesome. So again, very happy to talk to everybody here today. My goal here is to go over some slides. And for the slides, we're going to talk about the astronaut training program and the Artemis program. Also talk a little bit about myself and how I kind of got to where I am today. So again, there's about 26 or 7 slides or so. So I'm going to go kind of fast, but if anybody has any questions, you'll have to probably do audio because I can't see the screen. So that's welcomed. But again, I'll go somewhat quickly for the Q&A. So to start off here, the way that I grew up was all over the place. I was a military brat in the Coast Guard, and my dad, he is a Coast Guard officer. So most of the stuff, most of the places I lived was on the coast. So I was born in Florida, down there in the bottom right, specifically Miami, then moved to New Jersey, Connecticut, Virginia, North Carolina, did a little bit in Illinois when my dad was at graduate school, which I'll talk more about as far as graduate schools. Mostly I would say mid-Atlantic region area, right? So I've also traveled to many other states just in between, been out to California a few times for family and whatnot, but definitely all over the states. So I think as Lauren mentioned, she is a Virginia native. This is Western Branch High School in Chesapeake, Virginia. I really had fond memories here. And I felt like my personality and my qualities and skills was developed in high school. I feel like high school is the first simulation of life. You're going to have real friends, real problems, real challenges, real successes. It's a great way to test the waters, and it's okay to fail and learn how to recover from it. But like, high school is really kind of where you get your identity. And I won't say that it defines you as a person throughout your life, but it's a great place to start. But I had a lot of great experiences here, and it's very important to start off in a way that sets you up for many different options in the future. And I would say, to do hard things and complex things, you want to try to give yourself many options after that first choice, right? And so that you'll see a theme with that. But throughout high school, some of the things I was interested in was I was on the soccer team, played soccer throughout most of my life, was one of the co-captains, did basketball as well for high school on the JV side. I was a big chess player, so was also a co-captain of the chess team. So I always believed of trying to be like a Renaissance man with like, sports and music, art and things like chess. So trying to be as well-rounded as possible. And then also I had a passion for playing the drums. I was in the marching band, concert band, all throughout elementary school, different schools too. So again, as I mentioned, I was throughout many different states, but like one of the things that was really neat about it is when you're involved in a lot of activities, you can also develop things to talk about and relate with other folks that you're working with, to keep that consistency even as you're changing throughout different states. So I think this was important for me to have some sort of consistency in my life since everything was changing all the time. But these skills also come into play later on in life, which I thought were interesting. So that was kind of my high school days. And then for me, as Lauren mentioned in the bio, my first degree and experience was at the Coast Guard Academy. So for everybody's awareness, the Coast Guard Academy is similar to the Naval Academy, Military Academy for Army, the Air Force Academy, and a few other ones. So all of these academies, they groom people to serve in the military after they're done. And these are typically 4-year institutions where you pick up your, bachelor's, and you'll also get an officer commission. So when I got this was a $300,000 scholarship, and it was fantastic because they paid for the school, they paid for your books. You also get a stipend to get an allowance, a monthly allowance to manage your funds. A lot of great benefits there. That was helpful. Did somebody have a question online? I thought I heard something. Okay. If I didn't, that's okay. So this was a great opportunity to really learn leadership, get financially stable, and then earn that Bachelor of Science in Mechanical Engineering. Had a really good time there. Learned a lot and had a really good, I would say, colleague base, right? Because this is a small school. It was only 1,000 people. So we all got to know each other really well, and that carried really far into the future when you have really close relationships. So then after the academy, there was a lot of stuff that happened in between the academy and NASA, and I'll talk about that. But this slide just shows me doing some of the things at NASA that we do every day. The stuff on the left you'll see is that's the EMU, it's the Exploration Mobility Unit. And that's basically what we use to do spacewalks. And, as part of the training program, that's one of the major skills that you have to learn, which is very important. And on the right, we do a lot of flying jets as far as in the T-38, which is what it's called. These jets are both in the Air Force and in the Navy. And these jets, it's not just about flying something cool and fast. We actually have to learn how to work in pairs because there's a front seater and a back seater. And so we have to take turns flying the aircraft, talking to ATC, the air traffic controllers, and figuring out how to handle emergency procedures when like you lose an engine or you're low on fuel or you have some sort of a GPS issue. You have to work as one mind, because the analogy is when you're on a rocket and you're going through launch and ascent, and something's going on before MECO, which is main engine cutoff, and you have some sort of an anomaly, you need to act within milliseconds to work as a crew of 4 or 6 or however many are on that spacecraft and handle certain procedures. So flying the jets are a great analog for doing that, and it's a really great tool for us. So before I got to the NASA side, which I'll talk more about, I'll continue on post the academy. So after the academy, basically you become a commissioned officer. And in the Coast Guard, we're doing a lot of different things, right? We're doing search and rescue operations, we're doing helicopter operations. And I was also a naval architect and an engineer while I was in the Coast Guard. So all of that engineering I did at the academy was important and applicable to, as you see in the picture in the top right, trying to figure out how to save this, this vessel that was distressed off the coast of probably Hawaii. And how do we, bring the ship out of the water, pick it up without stressing it to where it collapses? There's a lot of different calculations that go into it. So there's a lot of neat things there. And then when I did the Coast Guard, I did active duty for about 7 years, and then I wanted to push myself and go deeper into engineering. And so I decided to go into the reserves for the Coast Guard, but then do something different full time. So I went to the Johns Hopkins University Applied Physics Lab, which was mentioned in my introduction. And here I was like a kid in a candy store because I grew up with a passion for like math and science. My favorite subjects were calculus and AP physics, AP calculus, AP physics. And like when I got to this physics lab, we were using that on a daily basis. It was fantastic. In the military, you use that math and science to kind of sanity check things that are already built. But when I went to the lab, I got to build things hands-on, go to the machine shops, take things in my mind, sketch them out, and then put them in CAD, 3D CAD modeling software, bring them down to the shops, either 3D print it or have it machined by people that I was working with, and put this out into an operational environment and test it, and then see it work operationally, recover it from the water using the ship life, and then basically make sure we iterate and grow and improve, right? So, on the top right, we had this device called a wave glider. I mean, this is so cool. It uses solar energy and wave propulsion energy, and it can basically stay out in the ocean for a year without being touched because it's just using renewable energy. I mean, it's awesome. As you look in that picture, in the shadow or at the top where the sun is shining through, there's this like 10-foot long by 2-foot wide surfboard that has solar panels on the top, and it has like a 25-foot tether that holds this submarine with 6 wings that articulate. And the reason this works is because as the ocean waves happen, the float on the top rises up and it drags this submarine through the water column. And when you learn about ocean dynamics, you have these orbits of water particles that are at the surface. At the surface, they're actually a lot larger than they are as you go down in depth. So because you have this large actuation on the surface and not a lot at depth, you're going to drag this glider through the water, and it's going to want to propel itself forward. So as long as you have waves, this thing can move itself without the thruster, which you also see on the back. And the thruster works off of the energy coming from the solar panels from up top, right? So as you see, like these systems that we're building, these autonomous drones, they're very complex, and there's a lot of multiple disciplines that you'll need to make these work. And so for me, being a naval architect, which is helping with the ship portion, getting the electrical engineering degree at Johns Hopkins, which helps me understand how to take acoustic signals and use digital signal processing to get them up to our payload and analyze the data. That's important. Having a mechanical engineering background to understand how to interface all the payloads in the surfboard, to understand the electronics cards, the heat sink, and all the connectors, right? How to do potting of material to keep it waterproof. Like having the multiple degrees wasn't just for kicks for me. It was very useful to put all this together. And then on top of that, to have the operational background from the Coast Guard, because we actually had to interact these wave gliders with the submarines that you see on the left. So we would use these wave gliders to triangulate positions of submarines so they can help improve the accuracy of how they use their ballistic missile system. And so by having an officer background and learning how to drive ships, going to the shipyards and understanding where the engineering, paperwork goes and how to talk to the right welders and the right integrators, like having all of those people skills, being a team player from, back in high school, being on soccer teams and chess teams and basketball teams, like all of that comes to play, right? So all of those skills from your early development come into how do you apply these to real life problems. So those, again, kid in the candy store, all this stuff was coming together late in my career, and it was fantastic. And I share this with you because you'll see how this applies to the things we're doing here at NASA. And then on the bottom pictures on the left there, it was neat because when I did my ocean systems engineering type stuff at Johns Hopkins here, we have a space sector. And so I was networking to be able to work my way into the space sector, which was my passion too, to do the double asteroid redirection test. So I was working in software. Like I think one of the ladies was talking about getting a computer science degree is super important because you can jump in anything. So when I got the electrical and computer science, kind of masters, gave me a skill set to then jump into fault management, which is writing software scripts on spacecraft to be able to make sure when the spacecraft feels an anomaly or it goes into an unsafe position, it can kind of put the spacecraft in a safe position to maintain the mission. So this double asteroid redirection test was awesome because we basically change the orbital period of a smaller asteroid around a bigger asteroid to prove that we can do planetary defense. So, I mean, it was fantastic. And then I'll kind of move a little bit quickly here because all of the different systems engineering type things I did, which I didn't know at the time was systems engineering, helped me realize I should likely look into systems engineering for the PhD that I got while working at APL. So one more plug I'll put on for APL, which is the Applied Physics Lab, is that they are a nonprofit organization. So they care about solving the problems for the problem and not the profit, which was important because they want to make sure their staff is highly credentialed as we have other contractors come in to utilize APL to sanity check designs or build novel things. And one of the things that they really advocate is to make sure that you have education. And so they will pay for your education full 100% covered by the lab. And that was one of the awesome little hidden gems that I found, just because I had no intention really to get another master's or a PhD, but when everything aligned like that, I said, why not? And it benefits me for the long run, which is also part of my plan to help get into NASA. So I share that because there are opportunities out there when you're looking at colleges and workplaces after that, start thinking about some of these things that might not be apparent to you, that certain workplaces can pay for your education. And you know, for me, I have 5 degrees and I've never paid a dime for any of them because the Coast Guard paid for the first 3 and then APL paid for the last 2. So it's something I like to share with people so they understand what's out there. So I spent a lot of time on that slide, but I think that was important for this type of audience. So hopefully that's helpful. We're going to jump back to the NASA piece because I wanted to kind of give you some background there. But getting into what I do now day to day is I support a lot of projects in engineering to support the NASA mission of going to Mars, Moon first, and then Mars. So one of the things we did here is we did an analog spacewalk out in Arizona. There's a place called the San Francisco volcano fields where there are 600 volcanoes. And it's crazy because we practice geology there for NASA. We take anybody who doesn't know geology, we basically send them out there to understand how to map all the different rocks and see if they can target, you know, rocks that come from certain volcanoes. And it's a great exercise. But here, it's a great place to practice, you know, how are we going to navigate on the moon with not a lot of, you know, navigational aids and land features. So this is where I was testing out some of the suits, which you see here. This is more designed for volumetric constraints and load-bearing constraints, right? So these suits were about 110 pounds. So they would try to simulate, hey, how fast will you move with a lot of mass on you? And they need to do that so we can time, you know, how do we plan 4 EVAs that are 8 hours long? Because we don't know how far can we go in certain places on the moon. And then we tested out some advanced concepts using, you know, holographic lens type displays for our maps and whatnot. So this was kind of just a little clip that shows you what we were doing out there. It was myself and then astronaut Kate Rubens. She's a biology major. We were a really great team working together. There I am pushing the cart, and she's doing the, you know, we take payload or panoramic views of cameras and we describe our terrain. And we did like a day pass where, you know, we do missions during the day to kind of see how things would work. And then at night, because at night, it's very different. And it's important because when we go to the South Pole of the moon, we're mostly night, I would say, probably 80% of the time. And that's really to keep a lot of the engineering constraints at a minimum, because trying to design for, you know, plus 250 C and minus 250 C is a huge challenge, right? So if we can go to an area that's just, you know, minus 250 C most of the time, we don't have to, you know, push the requirements that hard. So anyway, a lot of this prep is to help the users ourselves anticipate what we're going to experience and feel. And then for the planners of Flight Operations Directorate, like how do they map out where do we go for EVAs and how long it takes crew to do certain things. And also for us to test out the tool cart and all the tools and how do we do this dance of choreographing, taking samples and using hammers and all that stuff. So, I mean, it was really, really fun. I really enjoyed that. So that was one of the things that I did right after graduation, which was last March. And then on top of that, I got assigned to Artemis 2 mission as a backup to the US crew member. So I'm one backup to any 3 of the US crew members. And what we do as a backup is we prepare them for launch. So we have this role called the astronaut support person. And that astronaut support person is supposed to learn everything on the ground. So there's the ground system that we have here, the mobile launcher. That's where the rocket's going to be basically attached to before launch. And here, these are the escape baskets, the emergency egress baskets. And basically, if there's any sort of warning that the rocket's going to blow up and we need to egress people out, we have to ride down these baskets and basically get into these tanks. These are called MRAPs. These tanks will basically shield you from a blast as you're traveling from the rocket. This person here is Jenny Gibbons. She's an awesome crew member. She's also a backup for the Canadian astronaut corps. So Jeremy Hansen, which we'll talk about, he's the Canadian astronaut that's going to ride with the other three, and she'll back him up, and then I'll back the other three up. And these orange suits are the suits that the Artemis crew will wear when they're inside the Orion capsule. The Orion capsule is the capsule on the top, and then the SLS, which is the Space Launch System, is the big rocket that is on the bottom. So another thing that we did as a crew is we went to Iceland. We went to Iceland to understand, what's it going to be like on the moon to do geology. So we understand very complex features and landscapes, and we try to understand, okay, how do we look at basalts, which are certain types of rocks that we'll see on the moon. And two of the astronauts that have been to the moon, Jack Schmidt and Charlie Duke, they have been to the moon, and they said, hey, the most realistic or similar place to the moon that we have on Earth is Iceland. And so that's why they sent the Artemis 2 crew there to kind of get the training and also a bonding experience for us to make sure we can work well as a crew. So a lot of cool features here. There's an acid lake behind me that was very unique with a bigger lake in the background. I just really had a good time. So one of the things here, a lot of people ask why the moon. There's a lot of reasons on the screen, but really this is, I would say, our biggest testing bed before we go to Mars. There's a lot of talk right now about going straight to Mars and going to the moon. And I think it's really important to test how do we have our systems operate in deep space before we get there, and how do we test, some of the systems that we're going to use on Mars. But a lot of benefits due to inspiring a generation like you guys to continue to do STEM, which is very important, and bring back technologies for Earth that'll improve our life here. But honestly, we're trying to revolutionize the science and technology that's going to make us into a better species in the future, right? So there's so many reasons, but it's just awesome. So there's a lot of stuff here I'll kind of blast through, which is all the different system components, right? But Artemis program is really building a system for deep space exploration, right? So the moon and then Mars. So as I mentioned before, the SLS system is on the left. That's the big rocket that has the Orion, which is on top. You see in the middle top image, that's the Orion. Everything is stored in the VAB, which is the Vehicle Assembly Building on the bottom right. We have ground systems that are all over the world trying to communicate with the spacecrafts as they are doing their orbits around the moon and up to Mars. We also have a bunch of things like the landers that will be on the moon on the top left, all of our spacesuits and rovers. There's a new space station going on called Gateway that's going to go around the moon. That's going to be important to test things in those conditions that are in deep space around the moon before we go out to Mars, right? And at the end of the day, we're building this surface infrastructure in the bottom right that has big rovers, it has suits with people in them, and smaller rovers, towers, solar generation, all of that stuff. It's an exciting time. So, this is also kind of the mission profile right now. Artemis 1 happened in 2022. Artemis 2 is going to be the first crew for the program. And again, I'm going to back up 3 out of the 4. Artemis 3 is the first time we're going to land on the south pole of the moon, even though we've landed at the equator before. Artemis 4 is when we're going to build the Gateway space station. That's going to be orbiting the moon in a very elliptical orbit, right? And that helps provide a lot of communication time at the south pole of the moon, because we want to be able to hang over that area as long as possible. And then Artemis 5 is when we're going to have the lunar terrain vehicle. So there's a lot of moving pieces. Here's our crew here. Jeremy Hansen, the Canadian astronaut on the left. He's a fighter pilot. Reed Wiseman, he's our commander. He actually called me when I first got selected to be an astronaut and said, hey, do you want to do this? And I was like, yes. So it's really cool to serve with him. We've been doing a lot of different trips lately. Victor Glover is also a Navy test pilot, awesome guy. Him and I fly, as much as we can. And then Christina Hammock, she also is a fellow APLer. We went to Johns Hopkins Applied Physics Lab different times, but we can relate. She was in the space exploration sector too, but she's also awesome. Been to Iceland and the Arctic many times, and awesome rock climber. she's going to be the mission specialist. So if any of the three on the right go down, I will replace them. And I just hope that they don't go down. I really want to see them do this mission, and I'll support as the astronaut support person. So very exciting times. This is a picture of Gateway, of what it looks like. But the important thing here is that we're working with many different agencies. ESA, which is the European Space Agency, JAXA is the Japanese Exploration Agency, and then CSA, which is the Canadian Space Agency. You can see it goes even deeper to the contractors that are involved, right? And this is going to my concept of teamwork, right? From being on the soccer team, chess team, basketball team, having those activities allows you to understand what it's like to have, team dynamics and interact with people. Some of the jobs I did right before I got selected for Artemis 2 and after I graduated, the astronaut program involved suits. It involved the lunar terrain vehicle. It involved the pressurized rover and many other things. This last slide here is just to show you we had a lot of different countries that are supporting the Artemis program. And then at the end of the day, we came in peace in Apollo, and then for Artemis, we're returning for all of humanity. So the reason why we're pushing for, going to the moon and the Mars is so that we can all work together to really evolve as a species. So I just wanted to end it there. And I know that last bit was a little bit fast, but thanks for everybody listening in and then opening it up to questions. I love the chat, so I'll try to keep it efficient, but I welcome any question, all questions, and thanks again.
That was an amazing presentation. Thank you so, so much for sharing all of that. I have definitely got a couple questions for you, and if you don't mind switching so I can share, I can pull up my questions for you. Before I do, though, I really want to point out your wave glider work and how you did work with localization and all the acoustics, because that's actually what I got my master's dissertation. My master's dissertation was all about automating that and making it so
great
algorithms onboard those wave gliders. And I just think it's so cool that, two people in very different worlds of engineering end up continuing each other's work, and it just goes back to what you were saying with teamwork. So that's so cool.
Man, I didn't know that. We should definitely talk after this. This is great.
Yeah, we should. All right, let me go ahead and share my screen really quickly. 1 second, guys. Okay. Oops. 1 sec. I have to go back to the beginning of that slide. Try that again. Thanks for bearing with me, everybody. Computer issues are always fun to deal with.
No worries.
All right, there we go. That should be the can everyone see that?
Yeah, it looks good.
Yep. All right, we got there, guys. Thanks for bearing with me. So first thing I want to do is say thank you for all of your insights. And I was just kind of taking notes while you were talking and grabbing screenshots of all the students being so engaged in your presentation. I was really enthralled with your presentation. So again, thank you for coming out. And so these were the kind of key takeaways that I got from you speaking to us for 30 minutes. Lifelong passions and hobbies, they help teach valuable life lessons, take every opportunity to be able to learn more, and teamwork is beyond important. I left number 4 blank because I wanted to offer it to you, Andre. Is there anything else that you think is a key takeaway for your talk today that you really want to live with the students?
Yeah, I would say there's like 15 I want to share, but one of the ones that I think will be appropriate for this is that I really is a passion. You have to have the passion because you need to have enough in your bucket for when things get hard. You're going to have the extra mile, the extra bit of energy, because the stuff that we do is not easy. That applies in the training, that applies in the problems that we're solving, right? So if you think about it, as you're going through school now, the problems you're going to be solving 3 or 4 or 5 years from now are going to be a lot harder, right? So you're going to learn at a certain level, and then you're just going to have to keep grinding on that level to really succeed and do well. And again, if you're going to do hard things, especially in space industry, that passion has to be there. So that's important. And then one thing that I would say that's a goal one tactical thing that I'd like to share with folks is that when you have a goal, I think it's important to put a vector on the goal and not a straight line, right? And this is for this specific audience because you have the ability to kind of pivot in a direction. And so for me personally, like I knew when I was at age 7, I was like, I want to explore space as an astronaut. I was very intent on that, but I still thought that in general, exploring space is awesome. So my vector was exploring space, whether I did that as an astronaut or as a space systems engineer or as a scientist in physics or chemistry or mathematics, right? Like I wanted to go that way. And so like a lot of people ask me, man, you're in the Coast Guard. How are you going to do that? I'm like, well, I know in the back of my mind, that's giving me skills to go my vector, right? Maybe I'm using the Coast Guard as the moon to launch over to Mars, which is NASA. Like that's my analogy. So really having that vector in the direction of the general like passion, not necessarily tying it to a role, I think is important because you're going to develop relationships and skills that can allow you to pivot within that vector. So that's one of my biggest takeaways if for like career progression.
That's such fantastic advice. And again, just highlighting the craziness of me being the engineering presenter for your keynotes talk is my vector is actually ocean exploration and I'm using space to get there. So just wonderful passing of crossing of paths.
Yeah.
All right, so now I have some questions for you. A couple of these are from me, and then a couple of them are actually from students that have submitted them either in the chat today or earlier. My question for you is, what have you learned about engineering as a whole from all of your various test events? Because test events are so exciting to get to attend.
Yeah, test events are huge. And I say, first and foremost, they are critical if you really want to get the end solution right. The test events are the perfect feedback from the physical world to let you know, hey, your assumptions are valid or your assumptions were off or your material selection was a little bit different, right? All of that is important. And you should go into it expecting something to be off or different. And then one of the things about testing, I think, which is very humbling, is that we end up chasing perfection from the gate. We want to get our hundreds. We want to get 4.5 GPAs, right? And I think that's important so that you learn how to learn. But when you get to testing, all that stuff is off, right? There are going to be imperfections, but that's the best opportunities for learning. That's when the real learning comes in. And the more that you test, the more you're going to get that real world experience to understand, okay, I know this on paper looks like X, but when I go and I test it and I have to worry about electromagnetic, interference and radiation and all these other things to consider, it's not as simple as it seems. So it's very important.
Thank you. Okay, our next question is, what qualities does NASA look for in an astronaut? So what kinds of things did you put on your resume or your application that you think really made you stand out and led you to where you are right now?
Yeah, great question. We actually are going through our interview process as we speak, so this is very relevant. And I'll try to use the how do you say, most recent things that we are valuing. So in general, I think it's important to realize that if you look at what we're trying to do, we're trying to hire for people that will do their jobs in 20 years from when we hire them. So when you think about that, it really means that you need to be, I would say, a lifelong learner, because you're going to be constantly learning things until whatever mission happens. And that's going to be later in your career. And then we need people to be flexible and adaptable to be able to pivot with the way things are going in our organization and with whatever humanity is discovering. But the most important things I would think, at least for what we're seeing today, is, we're going to be going to longer missions, right? In the shuttle era, they had maybe 2-week missions. In the International Space Station, we have 6 months. They're likely going to 9-month missions, right? So you're going to be locked up in a bubble for 9 months or 6 months. And then if we go to Mars, right, that's probably 2 to 3 years in a bubble, whether you're in deep space or on the surface trying to build your bubble or build your cave, right? So you need to have good expeditionary skills. I'll say that one more time, expeditionary skills. That's what NASA is calling being a good team player, being a good human, being able to say please and thank you. You think this is very simple, but when you think about it, you kind of work with people over time. You know, when you get stressful, things don't get, easier. So when things go wrong, one of the biggest failures in the mission can be from the human. And we need to make sure that for you to stand out as a straight A student amongst thousands of people, if you have those personal skills and these expeditionary skills, that's going to help. And at a minimum, right, we have our baseline requirements, which means you have to have a master's now just to even apply. So there's going to be some tactical things that you'll need, like a master's, go to a good school, like have a good experience on your resume, and make sure that that experience is somewhat on the same vector of space exploration, right? And again, can be from oceans, can be from other industries, medical. And again, we also have different categories of applications from doctors, scientists, test pilots and whatnot. So again, there's a lot of basic things that you can find in your requirements, but the special things that we're looking for, which we do talk about, I think on the application, is handling long duration spaceflight and expeditionary skills. So I mentioned in my presentation all those different sports that I did and all the different clubs that kind of rolls into it. And so it's not as direct, right? But you have to find ways to make that fit.
Such a fantastic answer. Thank you. Third question, what role do engineers play in solving the world's biggest challenges? Or outside of this world's biggest challenges, I guess.
Yeah, it's fair. I mean, I would say the engineers are the trailblazers, I don't see, I think the business developers will be the ones that maybe are inspired, but like the engineers have to put the physics to reality, right? We're using physics and the math and the tools that were, provided to us from our predecessors to make things happen. So, we are the magicians. So it's really important for us to look at how do we achieve whatever business goal or company goal in a very efficient way with the resources that we have, right? And that's typically the balance. So when you think about getting to the answer, there's really never the answer. There's usually like a slew of 25 or 30 different answers, and you're trying to usually satisfy like 20 different stakeholders all at the same time. So you want to always be level-headed and you want to balance all of the different objectives. And so the engineer is really like, the air traffic controller trying to manage all these things and bring, again, physics to the problem. So that's going to be a critical role to make things actually work, because we can have all the ideas in the world, but if we can't put it down, do the sanity checks, make sure we're doing it right, and then test it, right, then we're probably not going to get there. And then I would say after the engineer, you have to have people who can then put their lives at risk and go do these things if that's what it calls for, right? But we're a big part, engineers are a big part of that process in the team too.
Great. And then I actually have this question was in the chat earlier from Ton Lee at MHS, which I'm pretty sure is a California school. So shout out to Pacific time zone out here. And
nice.
How impactful are the aerospace engineers to the mission success?
Oh man, very impactful. You think about it, I know earlier I kind of was listening, they talked about CFD, computational fluid dynamics, huge part of doing things for the space shuttle, huge part of even for our Artemis 2 heat shield. There's a big discussion about, we saw some anomalies in the structure in the foam, and we didn't know what was going on. And we used aerospace engineers in crazy simulations out at Ames to be able to figure out how, can we operate this vehicle in different trajectories to exacerbate the cracking or to not exacerbate that without these analyses and models, right? Which we can't necessarily test that again because we do a test every couple of years with Artemis. That accelerates our understanding of knowledge and risk posture, right? So being able to do these complicated analyses and understand your boundary conditions, your assumptions, and make sure you got the materials right, that all is super important. So, I mean, literally it has space in the name, aerospace, and we cannot do it without those folks.
And then I think we have time for one more question. So this is from Ramos High School. What has been the most fulfilling part of your whole journey of getting into astrodynamics?
So I would say it's a tough one. there's so many things that are awesome about just working in this position and then in the industry. But I think when it comes to, specifically astrodynamics and learning about orbital mechanics, I know from my space systems engineering courses and work with DART, double asteroid redirection test, I just really appreciate having the knowledge to understand how we can predict orbits and how we can predict and design missions. I think that's really crazy when you think about it, right? We're this little organism on this big planet, and we are like figuring out how to jump off to something else and intersect something or to land on something, right? And so, I mean, it's very awesome to see that we have the ability to do that. And when you learn astrodynamics and you get involved in that, to understand what it means for perigee and apogee and talk about, delta V required to get to X and what that, so you can really start to be a part of the solution when we have these hard tasks. And then you can start to think about, well, what would make space travel more efficient, right? Do we need nuclear propulsion? Do we need ways to, cut down the time it takes us to get there, right? You can start really leaning into improving humanity's strive for evolution, right? So that's what I really appreciate and like about having gone on this journey, because now I can't turn it off. I can't turn off. How do we get better, right? How can I now add to that? What new equation can change it? What's dark matter going to do, right? Like there's all these things in my head. So, but it's been great.
That paves the way for the next generation of aerospace engineers. I love that. Quick correction on my part. That was from High School for Health Professions and Human Services, and they are hard hitting with the questions today. They're doing.
Yeah, no, keep them coming. I know. Like I said, I wish we had more time. So, and I'll go as long as you want. Over. I got nothing after this. So.
Well, I think that was the last official question. And so we have 3 minutes left, and I just want to open the floor to you. What do you want to leave these future engineers with? What do you want them to be thinking about as they go into their tomorrow, next few years, and into their careers?
Yeah, I'd say I really liked the discussions earlier when I heard where, if anything, it's really good to start with engineering. You can really go anywhere from engineering, and to stay in it is awesome, because today we are approaching this, I don't know, technological acceleration with, artificial intelligence, new materials, new theories, new concepts. I think there's a lot of opportunity, and like I don't think you're really going to be bored. If you find yourself being a little bit bored because maybe something's repetitive, find ways to, get that fix, and either looking for new opportunity within organization, other organizations, right? Or build a skill. But man, there's just so much out here now that you really cannot be bored. So that's one of my biggest things, is like, if you start with engineering, you really can't go wrong. And it's just an exciting time to really be a part of the group. So it's awesome. It really is.
I mean, I'm excited just listening to you. That was such a wonderful, wonderful presentation. Thank you so much for coming and talking to all of these high school students. And thank you to everyone else for your wonderful contributions to this lab and this live lab day. I'm going to hand it back to Jillian to close us all out.
Awesome.
Thank you. Before you go, huge thank you to Andre Douglas. We're so fortunate to be able to learn from you today. And as Constance said, it was just really inspiring. And I speak for the adults and the students on the line. And fellow Virginian here, also from the 757 area.
Oh, wow.
Yeah.
Nice.
We actually have Western Branch participates in engineering tomorrow, your high school.
Oh.
Yes.
Wow. Okay.
Yeah.
Wow. Full circle. Never would have thought, right? But this is so cool.
Thank you so much. And Lauren, as always, a pleasure. You did an amazing job leading today's lab event. Thank you to the teachers and the students on the call, to ET staff for all the behind the scenes work that goes into putting these events on. I mean, can it get any better? Hope to see you next week when we have medical devices on the 12th. You don't want to miss that. Please submit those exit tickets and look out for an email from us with the recording of today, because you'll want to watch that keynote. Show it to all your other sections and classes, okay? Thank you so much, guys. You have an awesome afternoon. See you soon.
Thanks, everyone.
All right.